Thank you, Pam. Good morning, everyone. I'm Chen Zhao from the Australian Antarctic Program Partnership, University of Tasmania. Firstly, I want to thank you to the ICCI for giving me this opportunity to share my research here. And secondly, I want to say thank you to AAPP for supporting my team here. It's my first time in Seoul. I'm very excited about everything going on around. And today I'm going to talk about sea level rise and also how my research contributed to this. And before I start my talk, I want to introduce more about myself. I'm a glaciologist and also an ice sheet modeler. And my research interest is for the Antarctic contributions to the sea level rise using numerical models. So models are pretty my weapon, and my target is to try to explore the Antarctic methods from using the models. So my research is today more about the Antarctic sea level rise, contribution to sea level rise using numerical models. But as a modeler, I don't have too much chances to go to Antarctica for fieldwork. But luckily, I got a contract job as an expedition guide during my PhD. So I got a chance to visit a lot of polar regions and like Antarctic in the south, and Svalbard in the north, and Greenland. And I found those polar regions are fantastic. There are so many beautiful views there, the cute animals. But I also shocked by the coming events that happened in front of me. And all this kind of stuff just give me more and more motivation to continue my research on Antarctica. So that's why I'm here. And today I'm just going to share my latest research on the Antarctic contribution to the sea level rise. Okay, back to sea level rise. We all know that sea level rise is one of the most tangible impacts of the changing climate. And sea level rise is mainly caused by the melting of the ice from glaciers and ice sheets, and also the thermal expansion due to the warming ocean, and also the land water storage changes. But also we all know that the sea level rise is kind of moving a lot. If we look at this plot here on the left, you can see that since 1880, the sea level has risen about 21 to 24 centimeters. And this is a big number. And we know that in the past century, the sea level rise was mainly caused by the melting of the ice from the glaciers and the ice caps, and also the thermal expansion. But in the past decades, actually, Antarctic ice sheet and Greenland ice sheet contribute a lot, largely contribute to the sea level rise. So that's the point I want to make here. And if we look at the plot on the right, this is the average sea level rise in the past relative to the 1997 level. And we can see that the blue color means the sea level is rising. You can tell from this plot it's happening everywhere. Okay, those is some numbers I really want to share with you. We all know that a lot of people living in the coastal communities, they are facing the risk of the rising sea level rise and also the coastal flooding. And as we know that up to 410 million people living in the areas of less than 2 meters above sea levels, they are facing the risk of the sea level rising and also coastal flooding. According to our latest research published in the Nature Communications, we know that up to 200 million people in the world will live below the sea level line before the end of this century. An additional 160 million people, they will be affected by the higher annual sea level rise and also more rapid coastal flooding. And here I want to emphasize the impact of sea level rise on the coastal regions, especially for the small island nations. For those people from these nations, their sea level rise is much higher than the average. And this plot here on the right just gives us a general idea about where most people are affected by the rising sea levels. My country, your country, we are all suffering from it. So that's the reality. That's why we need to care about sea level rise. If the numbers are not enough, here's some very nice photos you may have seen before. And we know that sea level rise can cause more rapid increase in the tide and also the storm surge levels. They can push the water water further inland and cause more coastal erosion. So that's kind of very true thing for us to remember that the sea level rise is happening around us. And also I want to share the photo because I'm from Australia, and this event is like in 2016, there's like a wave up to 8 meters just hit the northern coast of the Sydney city. And this is photo where that event called in-ground swimming pool collapsed from the house that happened. Here is another photo shared from the Malaysian event happened just last year. So in 2021, the heavy rain just continued to affect the coastal city in Malaysia. And this event has never happened in the past 1 century. It just happened. And lots of people and infrastructure was affected by this flood events. So many things happen around us and happen more and more frequently just between you and me. So we all know sea level matters. We want to know more about sea level rise. That's what my research is doing now actually. So we know pretty well about the past because it's the data set we have from the observations. But to know more about the future, how much the sea level will rise in the future, that's very important for us. Okay, that brings me to my current research on the sea level rise projections. By seeing the sea level projections and back to the IPCC era 5, we all know that in that projections, the sea level rise projections were mainly based on the estimations of the observations and also accurate analysis. Because in that time, our physical models were not ready or not good enough to provide us more accurate sea level rise projections. But our ice sheet modeling community and climate modeling community, they have done tremendous efforts to make it happen. A latest attack was led by the IMAS 6. It's like the ice sheet model in the comparison project for IMAS 6. And it brings a group of international ice sheet models together for Antarctica and Greenland to provide their sea level projections from the different ice sheet models. And this one here I want to show you is from the 2100 years projections from the Antarctic ice sheet. You can see that these colorful lines are all the projections from different climate models. The thick lines are the mean average for each climate model, and each range is provided by different ice sheet models. We can see that the range here is pretty large. We can see there's a negative numbers here. That projection told us Antarctica was gaining ice rather than losing ice. That can be true based on our current observations. So I want to let you know that there are still large uncertainties in our current projections. But if you look at this purple line from the diagram 2, you can provide very large Antarctic estimates. I want to mention that our IMAS 6 results are mainly based on the past generation of the scenarios. So the team wants to provide more latest projections based on the new shared socio-economic pathways. So the team just combine the work from the Antarctic team and the Greenland team, try to combine this using the emulation of ice sheet models to provide the land ice projections to sea level rise under the new emission scenarios. So this is a map showing us what the land ice contributions before end of the 2100 years. And if you look at this up here in the main projections, if we could limit the global warming to 1.5 degrees, actually the sea level contributions can just be half, contribute to the result if we just follow the current emissions. And in these projections, we found that Antarctica is not sensitive to the different scenarios. They are totally same. But if we think everything in a very pessimistic way, that Antarctica's contribution to sea level rise could be 5 times higher. So this gives us this part of projections. Like what I just said, so the uncertainty is still pretty large in our projections, especially from Antarctica. So for our ice community, we still need to do more to contribute to provide a better projections. But luckily, for the first time, the IPCCR report, R6 report can finally use the results from the ice sheet models. This is what we saw here. Everybody here should be very familiar with this photo. And the top photo here is just showing us the surface temperature is going to be under different scenarios, and the plot on the bottom just gives us an idea about how much the sea level will rise before the end of this century. You can see that, I want to mention that as part of the estimate 6, we contribute to the medium confidence scenarios, and in that projection, the sea level will rise around 63 centimeters and 100 centimeters. That still create a big, large range. But here, what I want to emphasize is this, the dashed line. So, the possibility of like around 2 meters sea level rise before end of the century, or 5 meters before end of 2300 could not be ruled out, because there is still large uncertainties in our models, especially when it refers on the ice sheet processes. A lot of things still uncertain, so we can't be confident that it's less than 1 meter, because 2 meters might be possible. Okay, back to my current research. Early this year, the ESMIP 6 they just sent a call to our contribution to extend our experiment to another 200 years before end of 2200. The highlighted area is just what I did as our group to contribute to the second phase of the ESMIP 6. What we do is just use our ice models. Here we use IMAS, it's the model's name, and it's a finite element action model. We use the model to build a mesh, try to simulate how the ice flows on the ground. And here I want to mention that the plot on the right just shows us the current fastest glacier on the West Antarctica. It's Twist and Pavilion. So we try to use a very high resolution mesh to capture the ice flows near the ground line. So ground line, what I'm mentioning, it means is where the ice becomes flows from the ground. And then we try to simulate the very two key parameters in our model. One is the basal drag, how the ice flows on the bed of the ground. And also another key important factor is the ice viscosity. Those two parameters will be simulated by calculating the mismatch between our observed and simulated ice surface velocity. Once we got those two key parameters, we can use our model and then proceed the model by the forcing files provided by the institute, and mainly for CMIM 5 and the CMIM 6 climate models. So the plot on the right is how the forcing gives us the ice mass loss on the surface, and we can see that both green line is a purple line from the CMIM 6 model provides the more ice mass loss on the surface, and on the left is the basal mass flux. It's how much ice melting underneath the ice shelf. It's an output from our models. We can see that in the first 100 years, there's no too much difference between CMIM 5 and CMIM 6, but after 2100 years, you can see large difference. There are more mass loss predicted from the CMIM 6 model. So based on those two goals, I got our result here. As you can see in the plot on the right, this is our latest research based on the model. Result give us a general idea about how much the ice will contribute, the ice from Antarctica contribute sea level rise before the end of 2300 years. You can see that in our model, the green color is the low emission scenarios, other color lines all under high emission scenarios. No matter it's low or high, our contribution is always positive. It's not like what the ESMIP 62100 showed us. On Antarctic, it's always moving ice. But under our high emission scenario, we still have a pretty large range from 33 centimeters to about like 200 centimeters. And that I will give you not very extreme, but it's our simulations based on the highest mass loss from our experiment. It's the purple line I will show you here. And my PhD student V1 made a contribution to this animation. In this animation, it really shows us how ice flows on the Antarctic surface. And the color means the red means it flows very fast, can be more than 3,000 meters per year. And it happens just in Antarctica. So another thing I want to mention that please pay attention to the black line here. The black line is just what I mentioned, the ground line. That's where the ice becomes flows. It's very important for our ice dynamics because that's share the key message about how much the ice will flow from the ground to the ocean. So I'm going to play it. You can see that in the first 100 years, nothing happened in the East Antarctica, mainly first on the ocean glacier area. But after 2100 years, you can see everything happening. It's happening everywhere in Antarctica, and also in the East Antarctica, you can see rapid groundline retreat. And at the end of the 2300 years, you can see the three major ice shelves in the East Antarctica. Their groundline is very close to each other. It's very terrifying to see those three large glaciers, large ice shelves, to be going to connect each other. And another thing I want to mention that is in the East Antarctica. So I'm going to look into the East Antarctica because in the past few decades, there are so many attractions on the west part of Antarctica because we all know that they are losing ice very rapidly. But for the East Antarctica, something is happening now. And in our model, we can tell that in the first 100 years, holding ice shelf here is a ice shelf here. It's looking at very quickly in the first 100 years, but after the first 100 years, we can see some area like sorry, it's very hard to find the pointer here, but I'm in the work, and in this animation I just want to show you that thank you. In this animation I just want to show you that at the end of the 2200 years, in these glaciers their groundline just connect each other. That thing happened also for this Totten and its neighboring glaciers. What does that mean to us? Once the groundline connect each other, there will be more water, walking ocean water comes through beneath those new fluid area. That will lead to more rapid groundline retreat, means more ice loss from the ground to the ocean. That means more sea level rise. Another thing I want to mention is the Denman Glacier on the East Antarctica. Recently we found that underneath the glacier it has the deepest trough beneath the glacier, more than 4,000 meters. What does it mean to us? So once the groundline retreat back to the lower part of the trough, it will just lead to the rapid groundline retreat in just a few years. That means huge tons of ice lost. Okay, so what's the future of the East Antarctica? That's kind of one of the key questions I really want to do in my future research. Here's another plot. It shows us like the regional changes from the West Antarctica, East Antarctica in across 3 different time periods. If we just look at the top left is across the whole 300 years. We didn't see too much difference between East Antarctica and the West, but actually East Antarctica in most of our simulations contribute more to the sea level rise compared to the West. Although in the first 100 years we all know that in most of our simulations West Antarctica contribute more, but after the first 100 years, if you look at those two plots on the bottom, you can see that East Antarctica is the key role in the future sea level rise. That means we need to pay more attention there, but we have so limited observations in the East Antarctica. We need more work on East Antarctica. Okay, I have mentioned a lot of times about uncertainties in our ice sheet projections, so I want to summarize where are those uncertainties from. So there are 3 different sets of uncertainties. One is the physical parameters and also how we implement those physical parameters in our ice sheet models. So these key processes mainly include like the ice-ocean interactions, like how the ice and ocean interact with each other at the base of the ice shelf. Another thing is that the base of the grounded ice, how the ice flows on the grounded part of the ice. That will affect a lot. And some research shows us the subglacial hydrology will have a very dominant influence on the ice sliding on the base. And also last one is a very popular term recently. It's called the rapid ice cliff collapse. And this mechanism has been ignored in most of our action model simulations. The second one is our different action models, how we set up our models, how we what kind of boundary conditions this differ from each other. We need to find more about this. And last one is about the forces. Like what I just mentioned, the different forces provided by CV5, CV6, and how much confidence we'll have from those models. That's another big source of these large uncertainties. For myself, and in my future session, I will mainly focus on the two key processes. One is ice-ocean interaction. Another one is what I said, how the subglacial hydrology will affect the base of the ground ice. When I say ice-ocean interaction, I already sent one of my students into the oceanography, so I contribute to part of the ice-ocean couple modeling community. And in that research, we just use idealized domain to try to simulate how the ice-ocean interaction will give us a general idea about how fast the ice melts underneath the ice shelf. And in that research, we just did a research about what kind of choice we can have in our couple model setup. It's kind of very basic study to improve our projection in our sea level rise. Let's go to the next slide. Can we go to the next slide? Okay. Yeah, here is the last very fancy animation I want to show you. This is ocean simulations from a model called the Sharm shelf. Sharm shelf is a terrain following model. It can capture the features following the terrain and also can provide us obviously some process-based projections, mainly about the tidal-driven mixed melting. In this model, you can see. Can we play it? Oh, it should be animation, but it's not playing. But it's fun. And from this model result, we can get how the ocean surface temperature changed over time, and also how the ocean circulation evolves with time going. So in the future, we plan to just couple our ocean model from this product and also our ice sheet model, try to simulate the ice-ocean interaction while we did the projection in our models. So hopefully in the future we can have more confidence in our ice sheet projections to the sea level rise in our future project. So yes, finally I want to end my talk using the quote on our cover page of our State of Cryosphere 2022. If you have an interest in this, we have a copy at the reception. Please feel free to have one. And yeah, that's what I want to say. As the world leaders, we can negotiate the budget emissions, the different emission targets. But the one thing we can't negotiate is the melting point of ice. Yes, thank you. That's my talk. Do we have a question now or? Oh, okay. Yeah. So next we will have our speaker, Spencer from Chile. He will give us an talk. Thank you.